Let us now try to find out what is the daily energy incident on a tilted surface placed at a locality. So for that, let us first draw the horizon plane. So this is a 2D graphic. So the horizon plane is indicated as a straight line, and this is the horizon plane at some arbitrary locality on the surface of the earth. Now this axis is the normal axis, normal to the horizon plane. It goes vertically up, and this is called the zenith axis Z. This also we know. Normally till now, we used to have a horizontal flat plate collector, something similar to this. And for this horizontal flat plate collector, we were interested in finding the amount of daily energy incident on this horizontal flat plate collector. But in general, normally the flat plate collector is not kept horizontal at the locality. It is kept tilted at an angle, at an appropriate angle, which will collect the maximum amount of solar radiation. So therefore, if we tilt this horizontal flat plate collector at an angle beta to the horizon plane, so it will be tilted, the horizontal flat plate collector will become a tilted flat plate collector with the angle of tilt beta in such a way that the tilted collector tries to face the equator. In the northern hemisphere, it will try to face south, and the southern hemisphere, it will try to face north. Or in general, you can always say the tilt is in such a way that the collector tries to face the equator. I will now push this and try to bring it down to the origin like this. And also now let us draw a line normal to this tilted collector. So this line, this axis named N is the normal axis or a normal vector normal to this tilted flat plate collector, which is tilted at an angle beta to the horizon plane. Now it is of interest that we try to find the insolation vector which is along this normal. When the flat plate collector was horizontal, the normal and the zenith axis coincided, and therefore we were interested in the insolation vector along the zenith axis. But in actuality, now in the case of a general tilted flat plate collector, we must try to find the insolation vector along the normal to the flat plate collector, that is along this N axis. Now let me go back to the merged coordinate axis system. Recall that we have seen this merged coordinate axis system. This is the horizon plane, and with respect to the horizon plane, you have the local centric coordinate system shown in red. This is the south on the horizon plane. This is the zenith axis, and the one shown in blue is with respect to the equatorial plane, that is earth centric coordinate system. And you have the meridional axis and the polar axis shown like this. Now on to this, let us merge the tilted flat plate collector too. Now we have seen that the tilted flat plate collector is like this. We have the horizon plane at the locality, and we have tilted the flat plate collector at an angle beta with respect to the horizon plane, and the plane along the tilted flat plate collector is called the tilted horizon plane, and normal to the tilted flat plate collector, you have this normal line or the normal axis, N axis, which is orthogonal to this tilted flat plate collector. Now this one, let us merge it with let us merge the origin with the already merged coordinate axis system like this. After placing it like this, let us rotate it about the origin such that the horizon planes match like this. So the local centric horizon plane is like this, and with respect to the local centric horizon plane at an angle beta, you have the tilted flat plate collector, and the plane along that is called the tilted horizon plane, and the line normal to that is the normal axis. And it is now important for us to find out the insolation that is incident along this normal axis, and later to find out the energy incident on this tilted flat plate collector. So remember this modified merged coordinate axis system, and we will be using this to develop the equation for the energy falling on a tilted surface. As in the case of the energy on a horizontal flat plate collector, we have from the local centric coordinate system the insolation given as the insolation along the south axis of the horizon plane, insolation along the east, plus Lz along the zenith axis. So Ls, Le and Lz are given in terms of the zenith angle and the azimuth angle. From the earth-centric coordinate system, the insolation is resolved into Lm along the meridional axis, along the east of the meridian, and along the polar axis, and they are given in terms of the declination and the hour angle. Now, let us bring in the tilt also into the picture, and let us see how we get the modified insolation along the normal to the tilted flat plate collector. So we have placed here, brought in the modified merged coordinate axis system. Now this is the tilted flat plate collector, tilted at an angle beta with respect to the horizon plane, and this is the tilted horizon plane. And what is of interest is the insolation along this axis, the normal axis or the n axis, normal to the flat plate collector, which is tilted. So therefore, let us draw that, and I will name that one as Ln vector. And there are two vectors from the local coordinate, from the earth-centric coordinate system. One is Lm and another is Lp along the polar axis. So like as before, we will use the same method, and this is Lp. Now Lp will reflect on, can be resolved onto this n axis, Lm can be resolved onto this n axis in the following manner, knowing this angle. Now because this is beta, this will be beta, and therefore this will be phi minus beta, and Ln is given by Lm projected onto the n axis will be cos phi minus beta, and Lp projected onto the n axis will be Lp sine phi minus beta. Now we know Lm is L cos delta cos omega and Lp is L sine delta. Substituting, we have L into cos delta cos omega cos phi minus beta plus L into sine delta sine phi minus beta. Now this is the insolation equation for the insolation that is incident perpendicular to the tilted flat plate collector located at a locality which is at latitude phi from the equator. Now integration of this insolation ln over the entire day will give the energy on a tilted surface. So therefore, we can now find out the daily energy incident on a tilted flat plate, and that is nothing but H. We will now call it HOT. H naught, we had used that symbol for a horizontal plate, energy on a horizontal plate. H naught T, HOT, energy incident on a tilted flat plate, and that is equal to 2 times integral 0 to omega SR. Omega SR is the sunrise hour angle. Now I am going to slightly modify that. It will be omega SRT, sunrise angle for a tilted plate. I will discuss that more in shortly. And the integration is for ln with the integration parameter d omega. Omega is the hour angle. Now this would provide you with the daily energy incident on a tilted flat plate. Now let us perform this integration and then see what is the relationship that we will get. Now this HOT as given here has the units of kilowatt radians per meter square per day, because omega is in radians. Now to convert this into kilowatt hours per meter square per day, like as we did for the H naught case, we will use the scale factor. Now you have 24 K LSC. LSC is the mean solar constant by pi, integral of 0 to omega SRT, and ln we can expand cos delta, cos omega, cos phi minus beta, which is the tilt angle, plus sine delta, sine phi minus beta. Now this would be the energy expressed in kilowatt hours per meter square per day, because we have used the 12 by pi conversion factor. K and LSC have their usual meanings. So when you solve this, you will have cos delta and cos omega, cos phi minus beta are independent of the hour angle, and cos omega will become sine omega SRT plus omega SRT sine delta sine phi minus beta. Now this is the energy incident on a tilted flat plate located at latitude phi and having a tilt with respect to its local horizon with an angle beta. Now omega SR on with respect to the horizon of the place, we know is given by cos inverse of minus tan phi tan delta. Now if you take the tilted horizon, and I will call that one as omega SR beta, the horizon that is tilted at an angle beta, which we saw in the profile of the merged coordinate system, you will see it having a value cos inverse of minus tan phi will become phi minus beta into tan delta. Now this would be the sunrise hour angle with respect to the tilted horizon, which is tilted at an angle beta with respect to the horizon of the place at latitude phi. Omega SRT, what is omega SRT? Omega SRT is the sunrise hour angle for the tilted flat plate. Should remember that the sun should be the horizon of both the horizon of the place and the horizon of the tilted plane. Here you have the horizon plane and you have the tilted horizon plane, which is tilted at an angle beta with respect to the horizon plane. The sun should be above both the horizon for any effective Ln, that is normal insolation, to fall on the tilted flat plate. So not only is it sufficient that sun is above this horizon, it should also be above this tilted horizon. So if you take for example this horizon, which is having an hour angle omega SR, at some latitudes and some day of the year, the sun may rise above this horizon first and then above this horizon next. In the case of, in some other cases, you will see that the sun rises above the tilted horizon first and the horizon plane next, depending upon whether it is in the northern hemisphere and the southern hemisphere. So therefore, let us say the sun rises above the horizon of the locality, then we call it as omega SR. It has still not risen above the horizon of the tilted plane. When it rises above the tilted plane, you will see that the omega SR would actually be smaller measured from the meridional axis than what it would have been for the horizon plane. Therefore, what we do is we take the minimum of the hour angles as computed with respect to these two planes. Then we are safe, we are conservative, we know that there will be an effective insolation falling on this if we consider that the sun has risen above both the horizon planes. So therefore, what we do for omega SRT is to take the minimum of omega SR value computed as above and the omega SR beta value computed as with a phi minus beta value for the latitude angle. So therefore, whenever you use this relationship here for computing the daily energy incident on a tilted flat plate, the omega SRT, sunrise angle of the tilted sunrise hour angle for the tilted flat plate collector, use the minimum of the computation of omega SR as of the horizon plane for that locality, and omega SR beta for that locality. If you place a flat plate which is tilted at an angle beta, if you compute it like this, that is for the tilted horizon plane, that value. So these two values, the minimum of them is what has to be assigned to omega SRT.